So in the last video, we looked at the product rule. So if you had a function that was a multiplication of two pieces, you could think of one as being the first and the second and find the derivative using the derivative of the first times the second plus the first times the derivative of the second. Now we're going to look at quotient rule, and quotient means dividing. So if I have a function h at x and it's equal to something over top another, so we have something to do with x on top, we'll call it f at x, and something to do with x on bottom, and we'll call that g at x. And this only works, of course, if g at x is not equal to 0, since it's on the bottom and we can't divide by 0. So if you have a quotient function, then the derivative, h prime or h derivative, and now I'm going to think of f at x as the top and g at x on the bottom. So this becomes the derivative of the top times the bottom, subtract the top times the derivative of the bottom, all over the bottom square. So f prime times g, subtract f times g prime, all over g squared. And to prove this, I'm actually going to go back to our product rule and use that. Give myself some room. So we're going to start with the fact that we have a quotient function. So h at x equals f at x over g at x. And the whole point of this proof is to figure out what h prime at x is. Now, I don't know how to deal with a quotient yet, so I'm going to rewrite this as a product. Since g at x is dividing my f at x, I can bring g at x to the other side and multiply it. There shouldn't be a prime there. So all I have now is g at x times h at x equals f at x. That mark shouldn't be there. I know how to differentiate this using my product rule. So this side, because it's just f, will be f prime at x, and I'm going to use product rule over here. G is my first, h is my second. So the derivative of the first, g prime, times the second, h, plus the first, g, times the derivative of the second, h prime. So all I did there was differentiate both sides. Because this side was just f, the derivative is f prime. Because this side was a product, I use my product rule. But f prime isn't what we are trying to find. We are trying to find h prime. In here, I do have an h prime, and I'm going to solve for that. So h prime at x is equal to f prime at x. I'm going to take this g prime h over to the other side and subtract it. So I brought this term over and subtracted it. Now this g at x here is multiplying my h prime. So if I truly want to get h prime by itself, I'm going to bring this g at x to the other side and divide. Now, I've gotten h prime by itself, but the only issue with this, set it away, is that it has an h involved, and we want to define h prime using only f and g. But I know that h, if we go all the way back to our original definition, is f divided by g. So I'm going to take this line and replace this. So my h prime at x becomes f prime at x minus g prime at x, f at x over g at x, all over g at x. So all I did there from that step to that step is replace that h at x with f at x over g at x, because that was our original definition. Now, this is a fraction here, and this I'm going to ignore the g on the bottom. This f prime doesn't have anything under it right now. This part has g at x under it. So I'm going to multiply this by g over g. So I'll get f prime at x over g at x minus g prime at x, f at x over g at x. And I just realized I forgot my g at x here because I needed g at x on the top and the bottom, all over g at x. So f prime became f prime times g over g minus, that's the middle sign there, g prime times f, that's what I have here, over g. Now, everything's being divided by g twice. So another way of writing that is divided by g prime squared. Because if I divide by 2 twice, it's the same as dividing by 4. So because I'm dividing by g at x and then g at x again, I'm going to just say that's the same as dividing by g at x squared. My top here now is f prime g at x. That's this top here. This g's gone into the bottom. And I'm going to change the order of this one. So instead of writing it g prime f, I'm going to go f and g prime. And remember, this is what I got when I isolated. So that's the definition that I gave you right at the beginning, that the derivative of h is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So now we can do some examples. Let's look at h at x equal to 3x minus 4 over x squared plus 5. And we want to find h prime. We use the f and g notation, but I really like to think about it as top and bottom because that's a script that makes sense in my head. So now h prime at x is the derivative of the top, which is 3. The derivative of that is just 3, times the bottom, x squared plus 5, minus the top, 3x minus 4, times the derivative of the bottom, 2x, so I went and took the derivative of that, all over the bottom squared. Very rarely do we ever do anything with the bottom. The only thing we're going to do with this is FOIL and collect like terms. So I'm going to have a 3x squared from that multiplication minus a 6x squared, so that's going to give me a negative 3x squared. I'm going to have a positive 8x from over here because 2x times negative 4 is negative 8x, but because of that negative, it's going to be plus 8x. And then that multiplication will give me a 15, so positive 15 all over x squared plus 5 squared. So that's the derivative. So top and bottom tends to make a little bit more sense to me in my head. Okay. Let's look at one more example. So we have a function, f at x equals to 2x plus 8 all over the root of x. So this is a quotient function because we have a top and we have a bottom. But now they want to know where is the tangent to f horizontal. So tangent horizontal means slope of the tangent equals 0, which means the derivative equals 0, which means f prime at x equals 0. So if I can find the derivative and set it equal to 0, that will give me the points where the tangents are horizontal. So the first thing I need to do is find the derivative. I'm also going to rewrite f at x in a little bit different way to make it easier to deal with the root. The square root of x is the same as x to the 1/2 because remember, rational exponents mean roots. And now I'm going to be able to use power rule in order to figure out the derivative of this. So f prime at x is going to be the derivative of the top, which is 2, times the bottom, which is x to the 1/2, minus the top, which is 2x plus 8, times the derivative of the bottom. So the bottom is 1/2 x to the negative 1/2 all over the bottom, x to the 1/2 squared. So that's going to give me 2x to the 1/2. And now I'm going to multiply this through very carefully. So 2 times 1/2 is 1, and because of the negative in front, it's going to be negative 1. Then I add exponents. I have x to the 1 times x to the negative 1/2, so that's just one of my exponent rules. So I do 1 plus negative 1/2, so that's going to be x to the 1/2. Now I'm going to do the same thing with the 8. 8 times 1/2 is 4, and I have a negative in front, so that's going to be negative 4 x to the 1/2. And now x to the 1/2 squared, I multiply those two together, a half times 2 is 1. So that's just going to be all over x. Now remember, the whole point of this was to look for horizontal tangents. So I know that this has to equal 0. I'm going to deal with this x right away. This x is a dividing on this side. You can think about bringing it to the other side and multiplying, but 0 times x is still 0. Another way to think about it is that if I have a fraction, it doesn't matter what the bottom is. I need the top to be 0. So I'm really just going to work with the top here. So 2x to the 1/2 minus 1x to the 1/2 is just x to the 1/2. Then I have minus 4x to the negative 1/2. Well, there's a couple ways to deal with this. I'm actually going to go back to the roots because you might see that a little bit easier. So x to the 1/2 is square root of x. This is going to be 4 over the root of x because x to the 1/2 is root. And remember, negative exponents mean divide or move it to the bottom. We went over that in advanced functions. So now from that step, I'm going to find a common denominator. And my common denominator is going to be root x. So I'm going to multiply this one, which is over 1 right now, by root x and root x. So I get 0 equals x, because root x times root x is x, minus 4, because that one already was over a common denominator, all over root x. And again, I can either think of taking this root x over to the other side and multiplying. 0 times root x is just 0. Or I can say, if I have a fraction, doesn't matter what the bottom is, I just want the top to be equal to 0. So x equals 4. So that means at 4, we would have a horizontal tangent because f prime of 4 would equal 0. So your homework is on page 150, number 4 to 9, and number 11. But also take a look at the examples and take a minute to read through page 147 to 149 because it's just a few more examples of this quotient rule.